All right, I think we can get started. Now we have almost 60 attendees. It's quite a lot, and I'm sure a lot of more people are coming. So hello everyone, welcome to ASIC seminar series. I'm John, the seminar coordinator. And together with me is Miss Cassie Medley. So Cassie and I will be today's moderator. And our associate director, Ralph Ferrero, also joined us. And Ralph will be introducing the speaker before the speaker gets started. Just so you know, the seminar is being recorded, and the video recording will be published on our YouTube channel. So feel free to check out if you miss it or if you want to share it. And today we are excited to have our speaker, Professor Durran, joining us from University of Washington. Now, before he gets started, I'm going to hand this over to our Associate Director, Ralph Ferrero. So Ralph, please go ahead.
Yeah, I'm pleased to welcome our speaker, Professor Durran from University of Washington. And also this is our first seminar of the fall semester, so he is our first speaker. Professor Durran has done a lot of work in numerical weather prediction and has gotten into doing some deep learning type of work that we're going to hear about. A few other things about him. He's published numerous papers and a graduate level textbook on the subject, and he has been quoted in a lot of newspaper articles and so forth, and he's recently been selected to receive the prestigious AMS Jewel Charney Award, which he'll get in January of this year. So without further ado, I'll turn it over to our speaker.
Thanks very much. It's a pleasure to be kicking off your semester here today remotely from the West Coast. What I'd like to do is to talk to you about deep learning weather prediction and extensions to Earth system modeling. This is work that has been done with my former graduate student, Jonathan Venn, who really spark plugged the whole thing, frankly, but I was smart enough to pick it up after he left and keep going. Nathaniel Cresswell-Clay, a current graduate student, and Rich Cariana at Microsoft. And we particularly appreciate support from NVIDIA and the Office of Naval Research. Let's just recap something that you probably all have heard about before. Nevertheless, the story is that numerical weather prediction sort of had an early beginning in the early 1900s when Lewis Richardson tried to actually use a finite difference approximation to the equations of motion to integrate those equations of motion by hand and produce a weather prediction. It didn't work out, it turns out, so that was that for activity in the early 1900s, but he nevertheless imagined that if it had worked out, or if we could figure out the problems, that there could be some sort of fairly fancy setup where there was an actually purpose-constructed giant hall where people tried to forecast the weather, and there was actually a person with a hand calculator behind each grid point working away at this. But again, his procedure did not work out, which left us waiting for an advancement, which came in 1950. We had the first numerical weather prediction forecast made on the ENIAC, which was an old tube and wire computer shown in the diagram on the right. Jewel Charney and John von Neumann led the first numerical weather prediction experiment. And again, it was made practical actually by these advancements in computing and also actually numerical methods. The approach they used was different than the one that Richardson used back in the 1920s. And they solved, in the very beginning, this barotropic vorticity equation, which basically all you need to know about this is it predicts the behavior of the atmosphere at a single level based on previous data at that level, and basically was predicting 500 hectopascal height. Okay, so now let's ask ourselves, well, is the time right perhaps for a second revolution? Because things were enabled in the 1950s for NWP by these developments we talked about just a moment ago, and things have changed now. In the 2020s, we have possibly technological changes, namely the development of GPUs that are replacing CPUs in many applications. and especially any kind of artificial intelligence applications. And we've had advances in machine learning that are somewhat analogous to advances in numerical methods that taught us a lot more about how we might be able to do things in the future using something like deep learning to predict the weather. Okay, so I'd like to sort of focus on some of our earliest results. These are actually results that Jonathan Venn got when we were first starting and really got me interested in what's going on here. What we have here is a series of predictions of 500 hectopascal height using only 500 hectopascal height data. So this is back like what they were doing on the ENIAC. This first diagram here is a map of the 500 hectopascal surface at the initial time with a single contour highlighted in red, just to kind of help you as a reference. We have the verification 24 hours later in the upper right. And what we see at the initial time is there's a trough coming in on the West Coast, and it intensifies as it comes on shore, and the trough deepens into a closed low. Unsurprisingly, the barotropic vorticity equation doesn't manage to do this because it's a well-known defect of this model. It just translates vorticity or absolute vorticity around the planet and doesn't handle intensification, and so it misses the intensification. And this again is what the very first weather forecasts were based on back in 1950. And then if we look at the deep learning weather prediction model, where DLWP stands for deep learning weather prediction, we see that model actually did get the intensification, even though it was using the same data that we had available for the barotropic model data, only at a single vertical level. We don't actually have a dynamical explanation for how this model can do better, right? So the machine learning approach beat the available equation-based NWP. Of course, we can do better forecasts with NWP if we put more data into our model, but if we're stuck with just 500 hectopascal height, our dynamical model is the barotropic model, it does worse, as also shown by the color fill, which is the air. We can see more intense colors over here. And in fact, there's a second trough that behaves similarly further east. The intensification is picked up better by the deep learning weather prediction model. So I'd argue this is a pretty foundational result, really, that we will want to use going forward. The neural net learned to do better than an incomplete dynamical model. We know the dynamical model is not complete, but the neural net was able to fill in information the dynamical model couldn't come up with. And this is an idea that underlies a lot of use of deep learning to try to improve physical parameterizations in NWP models themselves, where we know the parameterizations are incomplete based on sort of somewhat ad hoc representations, and we're hoping that deep learning can do better. Well, this is something that might encourage you in that direction, except what we want to do today is talk about replacing everything with a deep learning weather prediction model, not just things like a cloud, convective cloud parameterization, for example. Okay, so I also like to point out that sometimes it's not entirely appreciated that there's a lot of empiricism in NWP. The NWP model consists of the dynamical core and the parameterizations, and we kind of think about the dynamical core first, and that includes the equations for conservation of mass, energy, and momentum. It covers the behavior of large-scale air currents in the atmosphere. We can analyze the approximation to the dynamical core using numerical analysis. But also operational models involve a lot more. The dynamical core in operational models is encrusted with parameterizations, and we need parameterizations for clouds and precipitation. And the sorry, is something not coming through? Or somebody need to mute? Are we all okay?
I cannot mute them for some reason.
Well, write it down. So
I'm sorry, I'm going to remove them from the meeting because I seem to not be able to mute them.
Well, I just wanted to be sure that I had myself gone off track. But
yeah, you are fine. I removed them. Sorry about that interruption.
Okay. No problem. All right. So anyway, the point is that we have parameterizations in global models and even finer scale models that cover clouds and precipitation, the influence of the Earth's surface where it's flat, the boundary layer, and also small scale mountains are also parameterized in numerical weather prediction models. And these parameterizations are evaluated empirically. So the rain we actually get out of the model relies on empiricism, not simply fundamental first principle equations. So that's a little bit like what we're dealing with, of course, with deep learning, which is certainly empirical. Okay, so while we're at it, on this same vein, I'd just like to throw out that sometimes people are worried that machine learning and deep learning, if it starts to become common way that we forecast the weather, is going to be the end of science or something like this. I think this is completely wrong. Because if we think about the relationship between science and the governing equations in NWP as we know them, there's no empirical justification required for consistent, stable approximation of the dynamical core. But we do need those empirically justified parameterizations that I was just mentioning to forecast precipitation and surface temperatures. And so there's empiricism in there. We can use the terms and the equations to do budget studies when we actually have an equation-based model, although again, we've got the parameters providing some input. However, if you actually have done budget studies with numerical models, you'll discover budgets typically do not close in full operational models, especially for things like energy, for example. So you can do budget studies, but they're not the be-all and end-all of the advancement of science. In fact, I'd argue we do a lot more when we use a hierarchy of models to produce scientific understanding. So we might start with full NWP models if we're really going after, a real-world event, which of course include the parameterizations. And then we try to link our results back and explain them with idealized models with simpler governing equations. And here governing equations really are the key to our explanation, because we have a simpler model that has removed a lot of these, or maybe all of the parameterizations. But even here, insight is not automatic. Just because we have got simple equations and a solution, maybe even, insight is not automatic. And as evidence, I would like to give an audience quiz. Can we derive the Coriolis force acting on east-west motions from conservation of angular momentum? This is something that you hear about now and then from different quarters. The answer is, so if we were in person, I'd ask you to raise your hands, yes or no. So you can mentally say yes or no. We know for sure that conservation of angular momentum is something that would happen if we were looking at hockey pucks, for example, moving around an ice-covered Earth. But the story is, no, we can't derive the Coriolis force acting on east-west motions from conservation of angular momentum, even though angular momentum will be conserved. So that's a bit of a detail, but I'm just pointing out that we shouldn't be too blasé about what we're going to learn just because we have an idealized simple model. We really need to get all the way to understanding in words, right? What we're really trying to explain about the atmosphere. And I'd argue that it's not apparent that deep learning weather prediction can't replace this part of the process, and then still we marry the rest of the results up with idealized models and so on and so forth, provided we have empirically verified the deep learning weather prediction model is producing the right answer. Okay, but this is a little bit like our use of parameterizations, right? So that's just a little bit of me on my bully pulpit here about let's not be too looking too down on deep learning models because they involve AI. So I'd like to talk to you about today now is parsimonious deep learning weather prediction. And we're going to use just a few variables in coarse resolution to characterize the atmospheric state for a few reasons. The most important one is that the space-time resolution required for NWP introduces more degrees of freedom than necessary to characterize most predictable atmospheric states on multi-week lead time. So I'm kind of looking toward sub-seasonal and seasonal forecasting with what we're going to do first with our model. And we don't have a lot of predictable degrees of freedom in that case compared to what we actually stick into an NWP model. For example, it's been demonstrated that for convergence, we need vertical grid spacing less than 200 meters. We want horizontal resolution less than 15 kilometers. And of course, that would imply that any convection resolving model has very fine vertical resolution. We don't really care about the solution every 200 meters in the vertical, unless perhaps we're doing aviation meteorology. We just got it there so we can run the NWP model in a correct manner. And it takes a lot of time. Okay, so like NWP, our approach will be to create forecasts by recursively stepping forward in time. And we use convolutional neural networks, and they are illustrated, hopefully, yeah, they're illustrated in this little animation here. We have a 3x3 stencil that we apply with the same so-called filter coefficients at every position on an XY grid, and we get some result back that fills in the next level of the neural network, and we do this again and again. And I'm not going to go into a lot of detail here, but those of you who recognize some of this will understand what's going on. Otherwise, just watch the picture. And we learn a lot of the coefficients associated with each one of these convolutions. We learn 6,428 or 256 sets of these filter coefficients, depending on where we are in the network. And we use a so-called UNet structure for our network. We train identical sets of filters, as I mentioned, for all equatorial faces. So there's no geospecific training of these filter coefficients in our model, except that we train different coefficients on the two polar faces, where the features in the atmosphere tend to move differently than they would in the tropics. And we actually train the same coefficients for both faces, but we flip the sense of rotation between the two faces, because as we well know that, the sense of rotation is flipped. Okay, I guess I threw something out of my talk. Is flipped between the top and bottom, between the northern and southern polar, the northern and southern polar caps. Okay, and this is just a quick look at the UNet architecture we're using here. We start with some data, throw it into several of these latent layers. We do some other stuff that I'm going to just kind of skip over. But the one thing I wanted to point out here is the net effect of everything that goes on. As we start with a single data point, when we do our first convolution, we influence a 3x3 set of values in this latent layer. We go through some latent layers, we do some average pooling, go through some more latent layers, do some more average pooling. When we get down to this corner of our network, our domain of dependence is 20x20 cells. So that single initial point has influenced a larger domain, and similarly, a single point at this point in the network is influenced by a 20x20 section of your incoming data. So that lets us see a larger piece of the globe than we would from a single convolution, for example. And this, we'll come back to this later, but remember, we get to 20x20 domain of dependence at this point, and we come on back up and make an actual forecast. Okay, so our fields are 2D on spherical shells, and we're going to start with a very simple model that has just 4 prognostic variables, something like surface pressure, 500 hectopascal height. This thickness relates to the mean temperature in the middle of the troposphere, and 2-meter temperature. We're not actually forecasting precipitation as a prognostic variable, for example. And we also input pre-prescribed fields, top of atmosphere incoming solar radiation, a land sea mass, and topographic height. And the top of atmosphere incoming solar radiation is varying as a function of latitude and time of day. It turns out we'll have 6-hour time resolution, for example. We're going to look at a model that has 48x48 grid points on each face of the cube sphere. So here's an illustration of the cube sphere with 20x20 resolution. We're using a bit higher resolution, giving us quasi-uniform resolution over the globe. That's 200x200 kilometers for each grid cell. Okay, and we're going to look at a free-running simulation, and we'll see how that goes, if it comes through the network smoothly or not. And this is the initial conditions for our free-running simulation. That is to say, we start on July 4th, 2017. I've got a plot of climatology on the right, because climatology is an interesting reference. It was, of course, the average weather on this date. Here's the initial conditions. Our model is tuned to minimize the mean square error over those 4 fields, normalized and scaled, over 1 day. So we're only looking a day ahead as we train our model, but then we're going to run it out recursively day after day after day. Our time steps actually turn out to be 12 hours to do this. And there's no physical constraints, remember, in the model. So let's see how this all performs. Well, the first thing we'll look at is the situation in January, 195 days into our pre-running simulation. Climatology is over here on the right. I didn't actually tell you last time, but I'll fill you in now that these colors are the 500 hectopascal heights. Of course, everything is smooth in climatology. The solid lines, the black lines, solid and dashed, represent this 1,000 hectopascal height or equivalently surface pressure. So we see here, for example, in this picture over here, is a ridge, a trough, a ridge in the 500 hectopascal height that of course are much larger in amplitude than climatology because this is from an actual individual time. We see that the heights have dropped here as we've gotten into winter. We've got bluish kind of heights in the polar regions, lower heights in winter than we had in July, if you remember. And then the question for you is, which one of these two is the free running simulation and which one is the actual data from that day? And they shouldn't perfectly match because there's no predictability 195 days. What we'd like a model to do is the same thing GCMs do, is if you run them out for half a year, they reproduce a plausible version of the weather. So there's some ragged, jagged lines here. That's from the linear interpolation we're using between the cube sphere and Latlon mesh. And we stopped doing that, but unfortunately, I don't have a nice set of updated figures. So things look ragged, and that's nothing to do with the quality of whether it's the real or the fake case. The simulated or the real data. Okay, so in your own mind, pick one of these two. Which one do you think is real? And I could try to get people to raise their hand or something, but I think all things considered, given the awkwardness of dealing with the Zoom, we'll just tell you the answer, right? But hopefully you picked an answer. And if you picked that this is the verification or the actual data, and this is the free running simulation, 195 days, you got it right. But the point here is that we've run this model step after step after step, tuned only to minimize loss over one day. And here we are half a year later, and we've got data that looks pretty real compared to the real case. It's actually slightly lower amplitude if you watch it long enough, but does a pretty good job and does not revert to smooth climatology. Okay, so now we'll see where we get on this. I'm going to go ahead and start this, and maybe you can tell me if it looks okay. Does it look all right, the animation? I'm not getting any feedback. Does it? You have black stuff, or is the animation?
Yeah, it flashed black. I think you have to toggle off the video.
Well, I got to try to turn my. I got to find myself here somewhere. There we go. Why can't I get my? I might have to actually get out of the display mode to get rid of my video.
I might be able to.
Okay, just eliminate my video for the time being.
I took your video off, but I think you'll have to. Yeah, I took your video off.
What's going on now? It seems like okay. There we go. Okay, video's off, so I think it's going to play better. Hopefully it is.
Yep, it's playing now.
Good. Just too much for Zoom bandwidth and whatever to handle. Okay, so what's going on here is we're just playing forward from that July 4th initial condition. So again, things are warm. We don't see any blues in the northern hemisphere. Here's climatology, the smooth field. Here is the forecast, which of course now is just a simulation way beyond deterministic predictability. Here's the verification. Okay, it's sort of moved its way while I've been talking into October, but let's get a little further ahead here to, here's December. You can see that top of atmosphere radiation has been enough to tell it to gradually move into wintertime. And we're getting these disturbances in winter that are more characteristic of a wintertime situation. And we come back out to April or even June, actually all the way to July. We just finished it. So it goes through the whole annual cycle. We're pretty surprised at this, frankly, that it does as good as it does, but it does, right? So we've actually been able to run this thing forward for a whole year. There's only a fairly minimal amount of drift in the whole forecast. So it's a very stable approach, turns out. The other thing, the next thing, start my video. Yes, okay. Okay. So you get to see my lovely face in the corner of your screen again. So now let's take a look at some other features that are interesting about this whole approach, which is that we've been able to do near surface predictions of that 2-meter temperature without any explicit boundary layer parameterization in a fairly reasonable way. So I'm going to show you results from a slightly improved model here that has 7 spherical shells of data. We had a total column water vapor, temperature 850, 250 hectopascal height, and we slightly increased our resolution to 150 by 150 kilometers. Okay. Okay, so we're going to compare daily temperature cycles at 2 meters in a 2-day forecast, and we're going to look at 2 locations. We're going to look at a pair of sites in the Amazon and the adjacent ocean and Australia and the adjacent ocean. And so if we go to the next screen, we'll see the results. So remember, we're doing forecasts at a 6 hour time interval. So we have a piecewise linear plot connecting these 6 hour values. The ERA5 data that verifies this forecast is dashed. The predictions are solid from deep learning weather prediction, and also the blue represents the ocean site, and the green represents the land site of the Amazon, or in this case of Australia, the red represents the land site. So we see, looking at this, is there's little temperature variation over the oceans, as we expect. The land sea mass surely helps with that. Shouldn't really be that hard to forecast. It gets it right. But the interesting thing, and we don't have sea surface temperature as an input, even to this day yet in the model, that we're dying to put it in. Is where we are now is kind of a complicated story, but we are going to put sea surface temperature in the model soon, which would be a sensible thing to have. But the key thing to note here, the reason I'm showing you this, is there's larger diurnal variations in Australia than over the Amazon, despite the fact there's no geospecific weighting, right? So it doesn't really know. Its filter coefficients, we're not trained to say, hey, this is the Amazon, and hey, this is Australia. We're using those same filter coefficients at all equatorial faces. Okay, so perhaps total column water vapor was part of the tip-off in this, but it understood the difference between what should happen at the surface over the Amazon and the Australia over a couple-day time period. And actually does a fairly good temperature forecast over the Amazon, or maybe not quite as happy in Australia, but some disaster there either. Okay, so I also want to move on. While we're talking about this specific model, the same model produced this deterministic forecast of hurricanes Irma and Jose. So this is the results of a 96-hour forecast. I'm going to try to show an animation in a moment. We'll see how that goes. But this is the 96-hour forecast. You can see what's happened is Hurricane Irma is here, and here's Jose. Here's Irma and Jose in the verification. So it does a pretty nice job on Hurricane Irma. There are other problems. I'm not happy about this low pressure center here, for example. This is still early days in machine learning, deep learning weather prediction, but it's interesting that we have managed to do such a fine job down here in the tropics at what is really in very, very coarse resolution. Trying to do this with an NWP model with 150 by 150 kilometer resolution, we wouldn't expect to capture too much detail in the hurricane itself. Okay, so I'm going to try to run the animation, and if maybe you should shut my video off remotely. That might be perfect. So we'll go for it here.
I shut your video off.
Okay, and it loops kind of fast. I apologize for that. You can see it's coming in 4 days from upstream of Hispaniola and all that over to the coast of Florida. Right? So the model does this, again, sort of amazingly good job for such a coarse model. Okay, so let's look at one other quick type of diagnostic. I'll restart my video here. We're going to look at diagnosis of precipitation with out-of-cloud microphysics parameterization. And this is almost the same model we saw before, except it doesn't have 250 hectopascal height. And if we look at what we've got here, I first will review for you a sort of a flow chart of everything that goes into making precipitation at the ground. You know, we start with water vapor aloft and cloud condensation nuclei, and a bunch of stuff happens, right? So it's hard to parameterize this even in a mesoscale model, let alone a global model. This is a typical mesoscale model parameterization, the WSM6. It's the most widely used parameterization for cloud and precipitation processes in the WRF model at NCAR. And it's got 6 species that are supposed to represent what's going on. It's got water vapor, cloud water, which is, say, liquid water that doesn't fall. It has cloud ice, frozen water that doesn't fall. And then it's got 3 falling species, snow, droplet, and rain. And there's a bunch of empirical relationships about exchanges between these 3 species. And if we were to look at what goes into this snow accreting rain process here, it's shown in the right. This is the formula for this, and it's got a bunch of stuff in it that, again, is pretty empirical. And I'm just going to focus on for a moment the fact that we have these, an intercept parameter, that's another complicated function, and we have a bunch of slope parameters that show up here. And we've got the 6th power, sorry, the 3rd power, the second power, and the first power, the slope parameter. And of course, there's other parameters. So there's a lot of empiricism that goes into this. It's tuned to do the best job it can, but it is very, very empirical. So let's just try it, if we skip all that, and just try to diagnose these 6 fields that I was talking about a moment ago on our 150 by 150 kilometer mesh. And we're going to work straight with the ERA 5 analysis now. There's not actually any model forecast involved here, except we could apply it diagnostically, the model forecast, but it'll have minimal error if we apply it to the actual ERA 5 analysis. And this is, again, we use a UNet like a regular model to train the diagnosis. And this is our verified precipitation from the ERA 5 model, which is not to say it's the real precipitation, right? Because the ERA 5 model is doing the best it can to represent the real precipitation. It's not easy, but you can see we've done a pretty good job of deriving the ERA 5 precipitation with our machine learning model. There are some unsurprising problem areas. The Sierras in California aren't captured at 150 by 150 resolution, but it's really pretty good, I'd argue. And similarly, here's another case. One thing I might mention is we're using a special objective function that helps us deal with the complex skewed distribution of rainfall. But anyway, the point being that we set aside all those parameterizations, we're able to get a fairly good rainfall forecast on this global scale. So we didn't necessarily need microphysics to get this. Okay, so now as we look especially out to longer lead time forecasts or even really short lead time forecasts, you want to think about ensembles. So one thing that's very nice with the machine learning models is they run super, super fast. I'll give you some details at the very end. So we made an ensemble of our deep learning weather prediction model, and we compared it to the European Center for Medium Range Forecast model designed for subseasonal forecasting. So that's a little coarser resolution in their daily model by about a factor of 2. And they verify their forecast twice yearly for their S2S, twice weekly over a year for their S2S forecast. So for 2 years, twice weekly is 208 forecasts over a 2-year period. We're going to compare against those forecasts with our model. So here's a contrasting of key model attributes. We have these 6 2D variables for the atmospheric fields. They have 9 prognostic 3D variables, 91 vertical levels. What that amounts to is 819 spherical shells of data. We've got 6. Our horizontal resolution is 150 kilometers. There's 18, 36 after day 15. This is again for their S2S forecast. We have 3 prescribed inputs for atmospheric physics. They have many physical parameterizations. We don't have coupling to the ocean and the surface, which is another defect. We use 10 ERA 5 initial conditions, which characterize uncertainty, but are not designed to capture the most rapidly growing modes. They have a more sophisticated singular value decomposition to set their initial conditions. We do perturb our convolutional neural network weights to make 32 perturbed models. We got that down here. We perturb the model essentially to get 32 sets of similar weights to give similar forecasts. So we sort of have a multi-model or a stochastic physics, you can see yourself, representation from these 32 stochastically perturbed weights. So if we take our 10 initial conditions times our 32 stochastically perturbed models, we have an ensemble of 320. They've only got 50. This is where we're ahead of them, right? We have a 320 member ensemble. They've got 50. Okay, otherwise they're ahead. And of course, their model does do better. You would certainly hope so, considering all the computing power that goes into it. But here's a plot of the root mean square error of the 500 hectopascal height globally averaged over the first 14 forecast days. So this is sort of at deterministic lead times here. What we have is a reference that's the climatological error. The error from persistence is the pink curve. And then the ECMWF performance is the dot dashed red line here. And our ensemble forecast is the green line. You can see, yep, we're behind, but we're not doing terrible. And in fact, even at 14 days, our ensemble has skill relative to climatology, almost nothing. But we keep our root mean square error below climatology for 14 days. So that's good, right? You want to beat climatology, and of course you beat persistence, which is not a very good forecast. Even in the beginning, it's not very good. If we look at anomaly correlation coefficients, a complementary score that penalizes you if your model just goes back to climatology, because it looks at perturbations from climatology. It looks at anomalies from climatology. In this case, better is a high score, right? You want an anomaly correlation coefficient of 1. And so the story is climatology gets a 0 because it doesn't understand where any anomalies are. Persistence starts out with the anomalies in the right place. Sorry, persistence starts with its anomalies in the right place, rapidly loses skill. ECMWF keeps the anomaly correlation coefficient score above 0.6, which is sort of sometimes thought of as the no skill threshold, out beyond 10 days. We keep it above 0.6, out beyond about 7.5 days. Overall, the story is a week ahead or so in the forecast for about 3 days behind ECMWF with a very simple model in both root mean square error and in the anomaly correlation coefficient. If we were to look at some further long-range forecasts in the S2S timeframe, we know right now there's very low skill in this period between, say, 2 and 6 weeks. If we look at forecast range and nominal skill in sort of a little schematic from White et al. The story is if we want to forecast rain tomorrow afternoon with a deterministic model, that works pretty well. But if we want, and it actually even seasonal outlooks, we have some skill from ENSO and other long-lived surface forcings. But in this S2S time frame, it's not clear what really gives us skill. We don't have a lot of it in our forecasts anyway. Maybe the MJO is the most important thing, for example. There are other possibilities that could be important as well. But let's focus on trying to use our model out in this S2S timeframe. So what we've got here are ensemble performance at S2S lead times, looking at the anomaly correlation coefficient of the ensemble mean from our ensemble, which is blue, the ECMWF ensemble, which is orange, and persistence, which is our measure against skill, right? Climatology has no skill in the ACC. We want to beat persistence. And the ensembles, and for that matter, the control from ECMWF are all beating persistence at both time frames, weeks 3 to 4, weeks 5 to 6. Note that we're actually not doing all that bad compared to ECMWF, especially out at weeks 5 to 6. The bars give us the anomaly correlation coefficient over our 208 test cases. The standard deviation produced by bootstrap resampling to get an idea of the confidence is given by the short black line. The very worst and the very best forecast, these 208 forecasts are shown by the dots here. So out at weeks 5 to 6, we're not really doing bad compared to ECMWF. Now, the anomaly correlation coefficient score is nothing to get excited about. It's a little less than 0.3, so it's not much skill, but it is still nevertheless true that the error bars actually overlap between us and ECMWF out of this forecast lead time. We'd like to see better forecasts from everybody, but we're sort of similar to ECMWF. We can also, actually, I'm gonna not bother to explain what CRPS is. I guess I'm gonna skip this explanation, but what it does do is it gives us a probabilistic score for the ensemble. So let's just let it go at that. We're going to look at a probabilistic score that takes in the information from the full ensemble rather than just an ensemble mean. And what we've got plotted here is a comparison between the ECMWF S2S ensemble and our deep learning weather prediction forecast of T850 in the global mean. This is a measure where lower is better. And so we see along the bottom here, ECMWF, the error bars are also pretty tight on ECMWF. They're the best, but on the other hand, the story is that, well, out of these longer time frames, out to week 4 and weeks 5 to 6, these are all 1 week averages. This is the average over 2 weeks, which is why this got a little better at this longer time frame for some of these models, including us and ECMWF. But we are in a statistical tie with ECMWF in CRPS for the global average T850 out of these week 4 and week 5 to 6. So again, we'd like to see better forecasts, but we are beating both climatology, which you can rank with CRPS, and persistence, as of course is ECMWF. Okay, And we still don't have SST in our deep learning weather prediction model, which is kind of dumb if you're trying to go out to sub-seasonal timescales. And of course, so the idea is we'd want to expand to evolve our deep learning weather prediction model into a deep learning Earth system model. And one thing to think about is we go all the way back to the ability of the machine learning model to figure out what the 500 hectopascal height should do when we didn't have equations that told it exactly the right answer, when we had to rely on the approximate barotropic vorticity equations, and the machine learning model did well. We see there's tremendous potential to put in non-traditional data directly into a deep learning model and train deep learning model on the non-traditional data. So for a deep learning Earth system model, for example, we would love to use, and are planning to make one that uses normalized differential vegetation index, which looks at the difference in the return in the near infrared and the red wavelengths of the spectrum up to the satellite. You can figure out whether things are healthy or stressed, depending on the value of this index. We can plot anomalies in NDVI, for example, and see the stressed vegetation in red here during the 2012 Great Plains drought. Satellite remote sensing is the future, arguably. And as we develop more long-term data sets, this is already a long-term data set, we can use machine learning techniques to directly train the machine learning model on these novel data sets, which will both give us an output the end users might want, as well as give us hopefully better forecasts, even things like the 500 hectopascal height. Okay, I'm going to skip this one. Well, yeah, I've got 1 or 2 minutes left. Let's just do the conclusions, and I'd be happy to take questions afterward, including the previous slide if you want to hear about it. But deep learning weather prediction has the potential, I'd argue, to revolutionize weather forecasting, echoing the impact produced by the introduction of NWP in the 1950s. And this is particularly important, or a particularly important aspect of this is that deep learning weather prediction can learn dynamics and physical parameterizations at the same time. We saw that earlier. And then this can be crucial for a system modeling and subseasonal and seasonal forecast, where some of the physical stuff we want to put in is stuff we do not have a good mathematical model for. The speed of deep learning weather prediction allows use of much larger forecast ensembles, like order 1,000 would easily be achievable with deep learning weather prediction. And a large, well-calibrated ensemble would better capture extreme events. Now notice, I said well-calibrated, right? Because just having a large ensemble doesn't buy you anything, but if we're able to get the ensemble to correctly represent the real world, then we really have a bonus when we want to find out what's going on with the tails of the distribution. About speed, the 320 member ensemble of 1 month forecasts that we talked about earlier can be stepped forward in 1 second on an NVIDIA A100 GPU. So we get all 300 members in 1 second. So what that means, of course, is we have plenty more than 1 second of time to spend. We can make our deep learning weather prediction model considerably less parsimonious, considerably more complicated, and still easily run a really large ensemble in plenty of time. Okay, and then deep learning Earth system models may be particularly appropriate for subseasonal and seasonal forecasting because it can directly generate end user products. And as it does so, actually hopefully improve the meteorological forecast as well. For sure, the state of the vegetation, for example, if we're thinking about NDVI, affects moisture fluxes at the surface of the earth and affects the weather. I'd argue that deep learning Earth system modeling can be the on-ramp to deep learning climate modeling. If we can show that we can do a good job on subseasonal and seasonal forecasting, where we can verify our results, that can help us get on to actual deep learning in climate modeling. So with that, I'll just put a slide up that does have the references to the 3 papers we published on this. This middle one talks a lot about the mechanics of the neural network, and the bottom one, sorry, the top one, the most recent one, talks about the use of the ensembles to do these long-range forecasts. So with that, thank you very much.
Thank you, Dr. Durran. So if anybody has any questions, you can either unmute yourself and ask it, or if you don't have a mic, or if you just don't want to talk, you can go ahead and just post it in the chat. I do have a question from Dr. Louis Uccellini from a couple minutes ago. Dr. Uccellini, you could ask the question if you want, or I can
Sure.
read it.
Sure. Can you hear me?
Yes, we can hear you.
Oh, great. Well, first, Dale, terrific talk, and congratulations on your AMS award, the Charney Award. Well deserved. So I asked the question actually as I was watching your sequence of models and noticing that the North Atlantic actually was suffering. And then you mentioned the SST, and as part of the question, I was asking if using an Earth system science approach would help, and you answered that at the end. So I have no further questions. It's just that I did note on your sequence that the North Atlantic was really suffering through the sequence. That's all. So
Yeah, we have. So you're absolutely right that we want to get sea surface temperatures and snow and ice cover and a number of basic Earth system inputs in, especially for these longer term forecasts. But for example, one thing we noticed is the period we covered in our paper. So it was the period covered by those CRPS scores had an El Nino. Well, we didn't see the El Nino. But obviously ECMWF saw the El Nino, and we need to be thinking even maybe more about even getting some more ocean parameters in there, and then we will of course have a deep learning ocean surface model anyway or something. So yeah, you're totally on target there. We need to get more information from the surface into this model.
So one other thing is when you were talking about revolutionizing the models, I've written some papers about the impact of numerical weather prediction revolutionizing the forecast process. I was trying to, like what's the step? What constitutes a revolution versus advancement? I think until I see the impact with respect to Earth system modeling, I would say that you're certainly advancing. This is really good stuff. But I'd be a little bit careful with that word, revolutionizing, at this point.
Well, it's a talk, not a paper, right?
I know.
So we have to stir people up a bit. But actually, I think there's first of all, actually, I should keep it short and say I agree, first of all, that the real revolutionary potential is in adding in more of these fields for which we do not need a forward model to put it into our forecast and then get something out, again, immediately directly out of the forecast without some other model that takes meteorological and geophysical variables and produces, vegetation stress. Or another good example would be wind power, wind generation. As we get more and more wind generation statistics, we can put that in the model, although probably won't ever have global coverage. But we can turn around and say that's a good input to our boundary layer information for the meteorology. Then we get out of it something the end user can use. So I think that you're right, that the real revolution would be to try to really couple in a lot of stuff that is difficult to put in current Earth system models and potentially can really help end users directly as output.
Thank you. I also have a question in the chat from Andrew Eichmann. He says, the tails of the distribution. Is there a concern with predicting unprecedented events that may not be present in the training data?
So that's an excellent question that we're actually trying to look at. In fact, we have a little project going on the side here. To the extent we are shifting the statistical distribution, and the events have occurred elsewhere on the Earth, I think we can have a good hope of catching them. To the extent that we are talking about something that never happened anywhere on the Earth, I'm not so sure, right? Because, and I'm not ruling out the idea that we would not at one point want to get some physical constraints into the model. It's interesting it does so well without them, but there certainly are physical constraints on a lot of things. And it may be that we will ultimately benefit from putting them in the model, which may help us a bit in terms of having confidence when we see some forecast that's way out in the tails. But I think an awful lot of what happens for most of the extreme events can hopefully be learned by looking at other portions of the Earth and then seeing a pattern that, in fact, would apply in a new area that is unprecedented. But it remains to be seen, and we're actually trying to test this.
Thank you. We also have a question from Dominic Stiller, who I just asked to unmute.
Thank you, Professor Durran, for the talk. It was very interesting. I'm wondering to couple the atmosphere model with a ocean or CS model. How would you include it in the neural network architecture? And would it make sense to somehow mix and match, for example, an atmospheric deep learning model with a traditional or numerical ice model, or vice versa? Would it make sense to have some kind of common interface?
So the first part of your question is, we'd use we've thought about this a lot, and we haven't coded it yet, but we've used two different time steps. We'd integrate, or we'd step forward the Earth system model on a coarser time step, using average forcing from the atmospheric model. And then we would assume that, let's see if I got that right. Well, anyway, you come together with separate time steps, averaging the forcing from the atmosphere on the Earth system model. And then similarly, we can kind of just keep the Earth system model stuff fixed for a few days in the atmosphere and step that one forward. So I think that we can couple them together quite nicely in a complete machine learning approach. And then we've been bad about this. It's something that's been on my list for years, but it's not even on the top of my list now. And yet it's such a sensible thing to do. One way to marry the machine learning models and the traditional models is with the grand ensemble. And it's kind of dumb that we haven't done this with the ECMWF model yet. And maybe we'll fire off a short little work in that direction soon. But that is certainly one way to couple these two things together.
Perfect. Thank you so much.
Thank you. We also have a question from Sheila Baber. Sorry if I said that wrong. I just unmuted her.
Amazing. Thank you so much. Thank you, Professor Durran, for your presentation. I am not coming from an atmospheric science background, but more as a land cover, land use geographical background. And my question would be in the land cover choice where you're running the model. I'm wondering how granular that needs to be. For example, if you are looking at weather across agricultural lands, would you have to differentiate between irrigated lands and rain-fed lands? And would you need to separate that from, say, forest cover? I know you mentioned snow cover as one of the variables you're taking into account.
Yes. So I think it does depend on what you're trying to forecast and what the scale is. At the moment, we're still planning to stay fairly coarse resolution. We're not really shooting in our current work for stuff finer than maybe 70 by 70 kilometers. So some of these distinctions start to be hard to really represent at that scale. And I don't really know. We'll have to see when we get there. But I think that I'm in sort of, if I could reply with a personal bias as opposed to science, I think that there's a lot of value in making a very faithful simulation of what's going on in some sort of run of the Earth system. So this could involve very high resolution weather and surface processes. Obviously this would be on the atmospheric side. It would certainly be convection permitting type modeling. Maybe some really fine scale interactions with the surface and so on. And this is all important. This digital twin idea. You've probably heard of digital twins. Make the digital twins as identical as possible down to the finest detail possible. But that's not quite the same as what you can predict. Right? So predictability is another issue. And it may be that some of these distinctions are really important for predictability, or maybe it washes out in the ensemble and it's not so important to have the fine scale information if you're looking on the S2S or seasonal forecast, or even out several days. It's hard to say, but certainly the shorter your time scale, the finer your spatial scale, the more all this detail matters.
Thank you. Also, Claudia Tibaldi's had her hand up for a while. So Claudia, go ahead. Oh, you were muted still.
Oh, I'm sorry. Can you hear me now?
Yes, yes, we can.
Yeah.
Go ahead.
Thank you. Thank you for your talk. I was curious about your comparison of skill between your neural network-based model and ECMWF. I know ECMWF is the gold standard, but I was curious just to get a sense if you took a less good weather prediction system, where would that system skill lie in your plots compared to the neural network and compared to climatology and persistence?
Yeah, we certainly can find setups we can beat. Okay, so I was thinking I might be able to get back to something here, but now I'm thinking maybe not. But there are coarse resolution runs of the IFS, which is the ECMWF model. Maybe I'll go ahead and we can beat some of them easily enough. But it's not entirely fair because the IFS is tuned for higher resolution, so their physical parameterizations could be off and so on. But we for example, in fact, we can beat a coarse resolution IFS. I think we currently have a model version I was just looking at this morning that I feel pretty confident would beat the same horizontal resolution IFS, which isn't where we were in our second paper. At that point, we had equal resolution, the IFS at around 200 kilometers, and our model, which is around 200 kilometers, that IFS was better. But now I think we can beat it actually at that resolution. So I think there are, this kind of game is why not just focus on the gold standard, kind of as you mentioned, but we can beat some models.
Yeah, that's the good thing about trying to emulate climate models, that you can always find a climate model that is worse than your emulator.
There we go. Right.
Thank you very much.
Sure.
Oh, John, do you have a question? Go ahead.
Okay. So Professor Durran, very impressive talk. Can you comment about the weather predictability? I know this might be $1 million question. For example, for the mid-latitude, there are some studies showing that the current weather predictability is has a limit about 10 days. Can you comment about the machine learning? Is there any potential or hope there to push the predictability limit ahead?
So I would say the answer is no, in terms of the deterministic predictability, right? So this is really a constraint that's in the atmosphere. It's not really so much a modeling constraint. The models, of course, can still mess up your prediction. I mean, models can screw up, of course, but the problem of air growth overtaking your prediction to the point where you're no longer better than a random guess compared from climatology. This is sort of how we think the atmosphere itself really works. That if you really had a real digital twin sitting out there over on the side, and you set up an almost identical situation, that after a couple of weeks, they'd managed to grow to be so far apart to be like climatology. Now, there may be statistical parts of the forecast from an ensemble that we can get skill out of at a longer time frame. So that's what we're talking about with S2S, for example. The idea is that as we start to put in surface forcing, we start to skew the statistics for weeks 5 and 6 away from climatology to have an anomaly that, if you average over that 2-week period, shows up as more rain or drier or hotter or whatever. So I think that S2S, so I think in order to do that, in order to tease the skill out of these longer ranges, we need to have a good representation of what the statistical distribution of possible states is, and then work with that. And the ability of the deep learning approach to allow us to make large ensembles and incorporate hopefully more accurately surface forces and stuff will hopefully allow us to have better statistics and better skill at those longer time scales. But I don't think we will do better short term, actually.
Got you. Thanks.
Does anyone else have any last minute questions? Although we're actually over time, so if you do, it's gotta be fast. Nope, okay. Well, thank you everyone for attending our very first seminar of the semester. And thank you to Dr. Durran for giving it. This was great. I hope that everyone returns because we got a pretty great lineup of seminars pretty much until Christmas, until the end of the semester. And if you're interested, you can just go to our website, news.essic.umd.edu, click seminars. You can see the whole schedule. So thank you, everybody. I'm going to be quiet and let us go along with our day.